Hello students, welcome to lecture 4 on the chapter Current Electricity. In lecture 3, we have discussed about derivation of electric current and derivation of electrical conductivity. We have also studied about Ohm's law, electrical resistance and electrical conductivity. In this lecture, we are going to discuss on factors on which resistance of conductor depends. Resistivity and its SI unit, electrical conductivity, and limitations of Ohm's law. Okay, now let us study all one by one. Factors on which resistance of conductor depends. Resistance of conductor depends on dimensions of conductor. Okay, what are the dimensions of conductor? Length, area, and volume are dimensions of conductor. Okay, these dimensions affect resistance of conductor. Nature of material. Even the resistance of conductor depends upon nature of material. For example, for pure conductors, the value of resistance will be different. For alloys, the value of resistance will be different. For alloys, value of resistance is different. Hence, resistance depends upon nature of the material. Third one, temperature of the conductor. Okay, let me briefly explain how it depends on temperature. Okay, if the temperature of the conductor increases, the atoms present in the conductor vibrates with maximum amplitude. Hence, there will be large number of collisions in the conductor, and due to this, resistance of the conductor increases. Hence, by this we can say that when temperature of the conductor increases, resistance of the conductor also increases. Okay, we have a very important point here. It does not depend on V and I. Okay, by this we get confused. Why we get confused? Because we define resistance with the help of V and I. But here we are saying that it does not depend upon V and I. For a given conductor, the ratio of V and I is constant. Now let me explain. When the potential difference across the conductor increases, then there will be increase in flow of current. When you take the ratio of V by I, then that ratio is equal to constant. Hence, by this we can say that resistance of a conductor does not depend upon potential difference and current flowing through the conductor. Okay, let us move on to next slide. Dependence on dimensions. Dependence of resistance on dimensions. Okay, to understand this, I am going to consider a rectangular slab of length L and cross section A. Okay, this is a diagram of rectangular slab. Okay, this is area of the rectangular slab and L represents length of the rectangular slab. Let V be potential difference across the ends of the slab, and that is shown across the length of the conductor. Let I be the current flowing through the conductor, and it is flowing along the length of the conductor. Now, by using Ohm's law, we can write V by I is equal to R. The ratio of voltage and current is equal to resistance of the conductor. Okay, I am going to use this as a reference, and then I am going to study how resistance changes with respect to length and with respect to cross-sectional area. Now consider two rectangular slabs of length L and area of cross section A placed side by side. Okay, in this case, I am increasing the length of the conductor. See, I am keeping cross section area of the conductor same, and I am increasing the length of the conductor. Okay, I have taken two slabs. That means I am increasing the length of the conductor and I am placing these two slabs side by side. That means the length of the conductor is increased. Okay, this is first one and second one is placed next to first one, and total length of the combination is 2L. Let I be the current flowing through both the conductors, and it is same for both the conductors. Why it is same? Because dimensions of or cross-sectional area of both the conductors are same. Let V be the potential difference across first conductor, and it is same across second conductor. Therefore, total potential difference across the combination is 2 times V. Okay, it is given here. I is current and 2V is potential difference across the combination. Again, by using Ohm's law, R dash is equal to 2 times V divided by I, that is equal to 2 times R. Okay, by this we can conclude that doubling the length of the conductor, resistance is doubled. Increasing the length 2 times, resistance is also increased by 2 times. Suppose if we increase the length of the conductor by 3 times, resistance of the conductor also increases by 3 times. If we increase the length of the conductor by 10 times, your resistance increases by 10 times. If we increase the length of the conductor by n times, your resistance of the conductor increases by n times. By this, we can conclude that resistance is directly proportional to length of the conductor. If length increases, resistance also increases. How they are related? They are directly proportional to each other. Okay, let this equation be 1. Next, consider a slab cut in two parts along lengthwise. Okay, we have a conductor and this conductor is cut along lengthwise into two equal parts, and length of both the parts is same and area of cross section is half of the initial one. L is the length, two identical slabs of length L and cross section area A by 2. The potential difference across these two is same and current flowing through each conductor is I by 2. Why I by 2? Because area is reduced and now the current is getting two paths, hence half of the current will flow through upper rectangular slab and half the current will flow through lower rectangular slab. Okay, now current flowing through each slab is I by 2. Potential difference across each slab is equal to V. Now by using Ohm's law, R double dash is equal to V divided by I divided by 2. That is equal to 2 times V divided by I, that is equal to 2R. Now by this we come to know that if the area of the conductor is decreased, resistance of the conductor increases. If area of the conductor decreases, resistance of the conductor increases. If area of the conductor increases, resistance of the conductor decreases. Hence, how these two are related? They are inversely proportional to each other. They are inversely proportional to each other. R is inversely proportional to A. Okay, let this equation be 2. Okay, now let me tell the significance of both. First, when length of the conductor increases, when length of the conductor increases, the electrons will undergo more collision because of length of the conductor, hence the resistance of the conductor increases. Similarly, if area of the conductor increases. If area of the conductor increases, the electrons gets more space to pass, hence resistance of the conductor decreases. By this, finally we can conclude that resistance is directly proportional to length and inversely proportional to area. Resistance of a conductor at a certain temperature is found to be directly proportional to length, that is R is proportional to L, and inversely proportional to area of cross section, that is R is inversely proportional to A. Combining these two, we can write it as R is proportional to L and inversely proportional to A. If I remove this proportional sign, then this equation becomes R is equal to rho into L divided by A, where rho is constant of proportionality, is known as resistivity. Even this resistivity is also called as specific resistance. Okay, you need to remember this relation, and it is important from the point of NEET and JEE examination. R is directly proportional to length and inversely proportional to area, and it is directly proportional to L and inversely proportional to R square, where R is radius of the conductor, and it is directly proportional to L and inversely proportional to D square, where D is diameter, and it is directly proportional to L square and inversely proportional to V, where V is volume of the conductor. Okay, next, resistivity or specific resistance. Okay, this resistivity is represented by rho, and the physical significance of this is it refers to the ability of the conductor to oppose the flow of current through it. It refers to the ability of the conductor to oppose the flow of current through it. Okay, it shows the similar role of resistance. Hence, we define resistivity in terms of resistance. We have R equal to rho into L divided by A, where L is length of the conductor, A is area of the conductor, and R is resistance, and rho is specific resistance. If length of the conductor is equal to 1 meter and area of cross section is equal to 1 meter square, then the resistance of the conductor is equal to resistivity of the conductor. Resistivity of the conductor. Resistance of the material is equal to resistivity of the conductor, or resistivity of the conductor is equal to resistance of the conductor when length of the conductor is equal to 1 meter and area of cross section is equal to 1 meter square. With the help of this, we can give the definition for specific resistance. Okay, now let me define. The resistivity of material of a conductor at a given temperature is equal to resistance of that conductor having unit length and unit area of cross section. I repeat, the resistivity of material of a conductor at a given temperature is equal to resistance of that conductor having unit length and unit area of cross section. Okay, this is the definition of electrical resistivity. Okay, note points to be remembered. SI unit of electrical resistivity is, okay, I have shown it by writing expression rho is equal to R into A divided by L. SI unit of resistance is ohm. SI unit of area is meter square. SI unit of length is meter. Meter and meter will get cancelled. And finally, SI unit of electrical resistivity is ohm meter. Second point, its dimensional formula is m raised to 1, L raised to 3, T raised to minus 3, A raised to minus 2. It depends upon nature of the material and temperature. Nature of the material. It means resistivity depends upon nature of the material. For example, for conductor, resistivity is small, for insulator resistivity is more, and for semiconductors it lies between the values of conductor and insulator. The material which has low resistivity is called as conductor, and the material which has high resistivity is called as insulator. And it also depends upon temperature. In conductors, if temperature increases, resistivity of the material increases. In semiconductors, if temperature increases, resistivity of semiconductor decreases. Hence, by this, we can conclude that it depends upon temperature of the material. It does not depend on dimensions of the conductors. It will not depend on length, area and volume of the conductor. It is independent of dimensions of the conductor. It is also expressed as rho equal to m divided by n into E square. Okay, this equation is very important one. Based on this, we will be telling temperature dependence of resistivity. Next, classification of materials on the basis of resistivity. Okay, we are going to classify materials based on its resistivity. Okay, first column represents material, second column represents resistivity range, and third one example. Conductors, the range of resistivity is 10 to the power of minus 8 to 10 to the power of minus 6 ohm meter, and examples are metal conductors. Semiconductors, the range of resistivity lies between 10 to the power of minus 6 to 10 to the power of 4 ohm meter. Examples are carbon, silicon and germanium. Insulators, resistivity lies between 10 to the power of 5 to 10 to the power of 16 ohm meter. Examples are rubber and wood, etc. Okay, based on these values, range of resistivity, materials are classified into three types. One is conductor, second one is semiconductor, and third one is insulator. Okay, we have another table in which there are some conductors, semiconductors and insulators, and the values of resistivity of those materials are given for a temperature equal to 0 degree Celsius. Okay, for conductors like silver, it is 1.6 into 10 to the power of minus 8 ohm meter. For copper, it is 1.7 into 10 to the power of minus 8 ohm meter. For aluminium, it is 2.7 into 10 to the power of minus 8 ohm meter. For tungsten, it is 5.6 into 10 to the power of minus 8 ohm meter. And for iron, it is 10 into 10 to the power of minus 8 ohm meter. For platinum, it is 11 into 10 to the power of minus 8 ohm meter, and for mercury, it is 98 into 10 to the power of minus 8 ohm meter. For nichrome, nichrome and manganese are alloys. It is 100 into 10 to the power of minus 8 ohm meter. For manganese, it is 48 into 10 to the power of minus 8 ohm meter. And for carbon, okay, carbon is a semiconductor, and for carbon it is 3.8 into 10 to the power of minus 8 ohm minus 5 ohm meter. For germanium it is 0.48 ohm meter, and for silicon it is 2300 ohm meter. And for insulators, for pure water it is 2.5 into 10 to the power of 5 ohm meter. For glass it is 10 to the power of 10 to 10 to the power of 14 ohm meter. For hard rubber it is between 10 to the power of 13 to 10 to the power of 16 ohm meter. For sodium chloride it is approximately equal to 10 to the power of 14 ohm meter, and for fused quartz it is approximately equal to 10 to the power of 16 ohm meter. Okay, these are the few materials, and this and their resistivity is given. Okay, these are the few materials given with their value of resistivity at 0 degree Celsius. Okay, next, let us see what is electrical conductivity. It is symbolically represented by sigma. The reciprocal of electrical resistivity is called electrical conductivity. The reciprocal of electrical resistivity is called electrical conductivity. Okay, let me tell the significance of this. It refers to the ability of the material to conduct electric current through it. It refers to the ability of the conductor or ability of the material to conduct electric current to flow through it. Okay, that is called electrical conductivity. It is mathematically expressed as sigma equal to 1 divided by rho, that is equal to n into e square into tau divided by m, where n is number density of electron, e is charge on electron, tau is relaxation time, and m is mass of electron. Its SI unit is mho per meter, per ohm per meter. Okay, instead of writing per ohm, we can also write it as mho. Per ohm is nothing but mho. Its dimensional formula is m to the power of minus 1, l to the power of minus 3, t to the power of 3, and a to the power of 2. Okay, this is the dimensional formula for electrical conductivity. Thank you.